Hello friends, MoNaCo with our fifth homework note video in atomic theory. We're going to be focusing on a very discrete skill today. It's called average atomic mass. And you're going to be able to use the relative abundance calculation, which is not in your reference table. So you have to know this process from your brain, not a reference, to determine the average atomic mass of all the naturally occurring isotopes of an element. This image on the first page here is showing you the average mass on our planet Earth of all the elements, showing that it's distorted. Hydrogen, carbon, and oxygen are the biggest ones. But we're going to get into how an average atomic mass for an element is calculated. So the connection here is what is a weighted average. And a weighted average is an average of a group of numbers that gives more importance to a subset of that number group. For example, if you were to find the average atomic mass of carbon 12 and 13, you right now might add 12 to 13, divide by 2, and get 12 and a half. However, that did not pay attention to the importance of one of those elements over the other. Not all isotopes of an element in nature are in equal quantities. Isotopes are atoms that have the same atomic number, but different atomic masses. So the great majority of carbon, 98.89%, is the isotope carbon-12. The remaining 1.11% is carbon-13. So your average would have to be adjusted to show that most of the carbon out there is carbon-12. Only a small bit is carbon-13. And we do the weighted average calculation in order to show that. That's what I'm going to teach you today. So this first image is about the average atomic mass, the weighted average calculation. It's the weighted average of an element's naturally occurring isotopes. So what you do is you take the percent abundance of isotope number 1 in the decimal form and multiply it by its mass. And then you repeat that for the next isotope and the next isotope, and you add up all of the results. You can see here that there's a little addition sign to add them all up. And what you get is an average atomic mass for the element. That is why all the elements on the periodic table have decimal values for their average atomic masses, because they have different isotopes that have different masses, and as a result, the average turns into a decimal. So for example, carbon, as I mentioned in our lead-in, has an abundance for carbon-12 of 98.89, and carbon-13 is 1.11. Let's take those numbers and turn it into the average atomic mass calculation, the percent abundance. So step 1, you take the mass of each separate isotope by its percent abundance in the decimal form. Do not screw that up. We have taken our 98.89% and converted it into 0.9889. That is the decimal equivalent of that number in a percentage. Okay? And the same is true for our 1.11%. We have converted that into 0.0111. How you do that, you might ask? All you really have to do is take your decimal place and move it 2 to the left to turn a percentage into a decimal equivalent. So you move your decimal place 2 spots to the left, you can turn any percent into its decimal equivalent. So then we've taken the 12 from carbon 12, that's the beginning, and the 13 from carbon 13, that's the beginning, and multiplied by that decimal equivalent and gotten a result. But you're not done yet. These are the weighted masses. All you have to do is add those together at the end. So add up the products of the calculated isotopes from step 1, and you've got your average mass. And if you check a periodic table, the average atomic mass of carbon-12, as reported by the IUPAC, is 12.0111, AMUs, okay, atomic mass units. Let's do some practice on these so you can see how I put them together. You'll often have 2 isotopes, but sometimes you'll get 3. So the first step is you multiply the mass by its percent abundance in decimal form. So for this first one, we got 10.0130 AMU. And I got to multiply that by the decimal form of 19.9. So I'm going to move that decimal place 2 to the left, times 0.199. Okay, I'm going to find an answer there. And then I'm also setting up the next one here, 11.0093 times, well, 80.1% turned into decimal form is 0.801. That equals these two answers. So answer 1 and answer 2. The last part you got to do is you just got to add those together to get your total final answer. I'd like to see you do that. You will need a calculator just to do the computation here. Okay? That computation's on you. I'm not going to do it in the demonstration here because it's, at this point, calculator math. Another example with 3 isotopes in play. Same exact setup. The first thing you do is you take the mass of that particular isotope and multiply by its percent abundance in decimal form. So looking in this square here, we got to find out where the mass is. The atomic masses are always on top. So our first number is real easy to go with. So we got the number 1 AMU for hydrogen multiplied by the decimal equivalent of 99%, which is 0.990. Put that in parentheses. Then we'll do the second isotope. It's 2 AMU times, well, we got to move this decimal 2 to the left. So 0.006. And then the third isotope, we take our 3 AMU and multiply by the decimal equivalent of 0.2 to the left, so 0.004. When you do that calculator math, you will get the weighted portion of each one of those isotopes as your answer. But you're not done, because the last thing you do is you add all those up to get your final average atomic mass. And the units are, of course, going to be AMUs. Okay? So, again, I'm not going to do the math for you because at this point it's calculator math and you should be able to do that. Right? That's a second one example with 3 isotopes. You might run into it at challenge practice where it's a word problem. Don't panic. It's the same exact 2 steps. The first step, you take your atomic mass for the isotope and multiply it by its percent abundance. This challenge practice wants you to work backwards. Honestly, I'm not going to throw that at you on the unit test or the Regents exam. That is a very challenging question here as I look at it. And I'd like you to skip it. No, we're not going to do the challenge practice number 3 because that is unrealistic for this level. That's AP level. Last little bit, let's take a couple notes here. The mass number is the mass of one isotope of a given element. The average mass is all isotopes of a given element. Okay? So mass number is one isotope. Atomic mass is average mass of all the isotopes. So at this point, the main point I wanted to point out to you was the atomic mass calculation from the average natural abundance. Okay, the average atomic mass and natural abundance can be used to set up a calculation to figure out the mass of elements, the average atomic mass of elements. And that is the major point. Okay, you again will not be expected to work backwards. You will only be expected to work forwards. Take the atomic mass, multiply by the percent abundance in decimal form, and you are golden. Thanks everybody for watching. Have a good day.